Hello, everyone. We'll be talking about small angle scattering experiments we did at APS and SNS, and it's X-ray versus the neutrons. And these are my group members. And just as an icebreaker, we'll be talking about a few dry jokes and bad jokes. So, who knows what happens to neutrons and X-rays when they get scared? Good job. Also, what did scientists say when they found two isotopes of helium? Come on, man. Yep. So our outline is we're going to talk about small angle scattering, and we're going to do a little bit of definition. We're going to talk about Sax and Sands, instrumentation, and do a little bit of comparison. And then we'll talk about some examples which we carried out, and then we'll conclude. So I'll hand over to Kai, who's going to continue.
So what is small angle scattering? I know that you have heard about it in many different talks in the past 2 weeks, but I'm going to talk it again. Bear with me. So as the name shows, like small angle scattering, when you get the angle, the scattered beam, and the incident beam and the scattered beam, when the angle is small, usually less than 6 degrees, we call it small angle scattering. And it is elastic scattering, and what we can get is that an elastic scattering intensity profile, and where the horizontal axis is Q, momentum transfer, which is inversely related with real space distances. So by looking at this region, we are looking at small objects in the real space. And by doing small angle scattering, we are more interested in the small Q region, which we look at larger objects in the real space. And by analyzing data in this region, we can get information about the size, the shape, and the orientation of structures in tens to thousands of angstroms. And these have a wide variety of applications, including chemical aggregation, polymer materials, and biological materials. And this is a schematic of the instrument we use at APS at 9ID. So what is interesting, what is important about this setup is we have 2 silicon crystals which has the same properties. Well, this one can give us collimated X-ray beams with a very narrow range of energies. And with the same configurations, the silicon will only count X-rays which has the same energies. So this basically gives us the elastic intensity. And what is special about this instrument is that they have a number of detectors which can change the detector to sample distances. And this allows a wide range of Q values to be detected, to be accessed. And this will allow simultaneous collection of ultra small angle scattering, small angle scattering, and wide angle scattering. So wide angle X-ray scattering is basically X-ray diffraction.
All right, so now I'm going to talk about the neutron side of the instrument. So the SANS guides that are at a continuous source, they use a cold neutron source, which is usually supercritical hydrogen or heavy water, depending on the reactor that you're at. So first, the neutrons, they start at the reactor. They go through this velocity selector, which is basically like a turbine that's rotating really fast or at the correct speed to only allow neutrons through that are at a specific velocity. And that's how you control your wavelength. At HIFER, the resolution of the velocity selector is about 10%, and that's one of the major resolution limitations of this instrument. So once the neutrons have gone through the velocity selector, they go through these neutron guides, which basically operate off of the principle of total external reflection. They're just like super mirrors. And then they go through a couple pinholes, which defines your beam spot size. At HIFER, they can control the size between 2 and 26 millimeters. And then it goes to an area detector, which is made of helium-3 gas. So when a neutron interacts or collides with a helium-3, it splits it up into hydrogen-3 and a proton, and then those two species have chemical or kinetic energy associated with them and can be picked up by the detector. So this is an aerial view of the SANS instruments at HIFER. So the neutron guide is in this area here. The velocity selector is somewhere around here. Your sample goes in a sample holder right there, and then this is a big vacuum chamber that holds your detector at the end. So the neat thing about this is they actually have two detectors, one that's close to the sample right up here. So you actually get wide angle neutrons that are scattered off in addition to the small angle neutrons. So the small angle detector is at the end of this chamber here in the back, which I can show you in a zoomed in picture right here. So the sample detector is right here, and there's actually a cool window here that was already shown on a presentation an hour ago that you can look into and see the detector in the back. Which is back here. And this little thing in the middle here, that's the beam stop. It's a boronitride that absorbs a lot of the incident beam so you don't damage your detector. And then the wide angle detector is not on the screen here, but it's close to the position of the camera. And moving on.
Yeah, so the basic theory of small angle scattering is that your intensity is plotted as a function of the form factor over here and the structure factor. So form factor relates to the shapes and size of your nanostructures, and while the structure factor relates to how these particles are packed together in your sample. This part here is the difference in your contrast. In case of X-rays, that would be or difference in scattering length density. So in X-rays, that would be the electron density, and in SANS, it will be the scattering from the nucleus itself. So you've seen this previously, right? I just want to reiterate that at high angles, or high Q, you're probing smaller structures. So that kind of relates to the in intermolecular bonds, and going to lower Q, you're going to small particles or primary particles, aggregates of these primary particles, and aggregates of these aggregates to these large agglomerates. Oftentimes, this is kind of like the USAX region, SAX region, and beyond this is the wax region. One of the, I guess, big difference between SAX and SANS is that there's this contrast matching that you can play with SANS. I know that's been mentioned a lot, but it's essentially because isotopes have different scattering cross-section than the other isotope. You can play around to essentially with the scattering length density, and you can tune your sample to be able to see what you want. So, and it kind of solves a lot of the phase problems that you have, because, whether you're seeing red in blue or blue in red, these two would actually would give the exact same scattering spectra.
I'm going to talk about the same slide. All right, so we did a pretty fun experiment. We did a tri-block copolymer micellization, and we studied the effect that temperature had on it. So we took this tribrod copolymer, which has two hydrophilic ends and a hydrophobic middle, and we basically changed the temperature and looked at what happened. So we used two models to fit. One of them looks at one polymer crystal in a solution, and the other one looks at an actual tribod copolymer micelle sphere. So we used these to fit our data and to see what was going on in the system. And so below the CMT, which is your critical micelle temperature, you wouldn't expect to see micelles, and so the fit of a Gaussian polymer fit really well, indicating that no micelles were formed.
Thanks. Okay, so this graph comes from a result of at temperature 20. I'm sorry. Can you hear me? Yeah, that's fine. So at degree 28 degrees Celsius, just right above CMT, the critical moistness temperature. And you can see in this graph, there are different colors, and though at the two ends there are data points with very poor statistics. That is, the reason is just that I made this graph, and different people have different appetite for colors and markers. So I use different things, and as a physicist, you don't want to drop any of this reasonable data point. You leave them here to let people trust you. This is a real data, and you only fit the central part. And you can see it's quite different with the previous one. There's a peak here, and this is the signal that you see the concentration, you find the micellar, and you can see if you use the same model you're using below the critical temperature, it will give you a very poor fit and can't reflect the right shape of this curve. So you turn to another model which is designed for this tri-block polymer, and you get this very good fit. And yeah, in fact, it used to be a graph with the same color as the previous, but I just don't like it and change it to mine because sometimes you really don't like other guys' fit and you see this one is better and I will use mine, and that's it.
So we had, so basically the three things we got out of here were you could measure your polymer radius. We estimated a micelle diameter, so we took the radius that was calculated and just added it to the shell radius. And then we also got aggregation numbers. So you can see that as temperature increases, your aggregation number increases. And then below your CMT, which is about here, you have single polymers, and above it you have micelles.
To give you an idea of some other things we can do with Sacks and Sands, we looked at some commercial products, toothpaste. These are going to be aggregates of a whole bunch of different materials, of abrasives and flavors and different treatments for your tooth. And this is looking with probably the wide angle detector of the Sacks machine we used. You can see the diffraction peaks. And this is useful when we have so much going on. It's not going to be that easy to fit a particular model to see like one size of one material, but we can compare to see if they have the same ingredients or if they have an ingredient that we're particularly looking for. So we fit Crest and Sensodyne, and then we looked at the Colgate, and we found it lies directly on top of one of the others.
Finally, we get to the conclusion part, and we have to say Sacks and Sands are powerful techniques for characterizing mesoscopic structures, typically 1 to 100 nanometers. And Sacks is great for soft matter. Sands is great for soft matter, such as low Z elements. And Sacks is great for everything else. And the collection is very fast. And we also want to speak loudly. Neutron and Actrin School is awesome. You agree with me? And at the end, acknowledgement. Okay, thank you for you guys listening.
You have like a set of data that like are these all unique solutions when you get these?
No.
How do you deal with that? Do you use like other techniques to kind of Well, yeah, I mean, it's part of the phase problem too. So it's you know, if you imagine a cylinder that's have a pretty really that's short. The length is comparable to its diameter. Then it kind of looks like a ball too. So in that case, you can fit a cylinder to spherical particles as well. But it's usually you have some a priori knowledge of your sample, right? Like if you're making gold nanoparticles, like you can image them in a TM and you know, okay, these are spheres. But what the small angle scattering allows you to do is it allows you to probe them in dispersion. So when you're studying, for example, the structures that perhaps like they're forming certain shapes of aggregates in dispersion, you can't really investigate that with TM because you have drying effects when you deposit them onto the grid.
How would you suggest we get the contrast matching on sets? Is there a way to do that?
Not that I'm aware of.
Can we introduce any kind of?
You can use resonance scattering, so you can adjust the wavelength in different. They've done with tribox, so you can do it at different edges and basically contrast match the edges.
Okay. All the examples you give, and most of the samples people look at are radially symmetric. They're powders or something just average around rings. But I could imagine that you could have a case where you have a flow cell or magnetic field or something, you have anisotropy. Can you measure anisotropy in sacks and sands? Is one easier than the other, or?
Yeah, anisotropy can be measured. That would be when you have an anisotropic structure that would appear in your Sachs curve in a difference depending on the slope. Typically, you kind of you kind of know what sort of using I guess common sense or from theory what kind of shapes they're forming, and you fit those to a model. With regards to Sachs and sands, I think it can be done in both. There's really, apart from the mechanism of contrast, I don't see too much of a difference in technique between the two.
Yeah, the only other difference I could imagine is the detectors might have better resolution in one case or something.
Yeah.
I don't know.
Do you get radiation damage to the sample for the synchrotron states?
No, I don't think so.
Depends on your sample, but usually for materials, no. But for biological samples, I know that's a problem.
Okay, let's have this go together.